Power quality issues cost industries billions every year, and most of them never get properly diagnosed. If you work in the field, you know the frustration. This podcast is for you. Welcome to Power Quality Decoded, brought to you by Power Monitors Incorporated. Find us at powermonitors.com. Let's dig in.
Hello, everyone, and welcome to today's white paper webinar. And today we're talking about interharmonics and how interharmonic frequencies can cause a continuously varying RMS voltage. The fact that they're not synchronous with 60 Hz, you get an effect where the RMS voltage is different from cycle to cycle. This doesn't happen with harmonic distortions. It's not inherent in waveform distortion that you get this RMS variation. It's something that arises when you have non-synchronous frequencies present. Landon here with me has written an interesting white paper on a mathematical treatment of this issue and how it relates to flicker. So I'll hand this over to Landon.
Hello. Basically what I've done is I've used the standard root mean squared calculation, and we assume that a signal can be broken up into a sum of a bunch of different sine waves here. So we can do as many sine waves as are present in the signal. I apply this sum of sine waves into this RMS formula where we square it, integrate over time, and then divide by the period, and then take the square root. So equation 1 is just plugging this sum into this expression. Equation 2 is simplifying this a little bit. So I'm squaring everything, writing it as the RMS squared, rearranging the sums in the intervals. I'm factoring out all of the amplitudes of the sine waves, and then we're just left with this giant expression. And the main part of this expression is this. We have an interval from x minus 1 up to x of some random sine wave times another random sine wave. And so this is mainly what I'm analyzing is this integral, this inside integral right here. And that's written out in equation 3. So equation 3 is just integral over a one cycle time period of a sine wave times another sine wave. And then after and plugging this into a computer algebra system and going through a lot of algebra steps, we end up with equation 5 right here, where this f is defined to be 1 over m times the sine of m over 2 times the cosine of m times x minus 1 plus b. And so we have the difference of the two frequencies. So there's m sub I and m sub j right here. So m sub I. So this term here is m sub I minus m sub j. This term is b sub I minus b sub j. This term is b sub I plus m sub I plus m sub j. And this term here is b sub I plus b sub j. So we're taking the difference of the two parameters here, and we're taking the sum of the two parameters here. And then this expression here has a lot of interesting results. If I go to my graph here, I have one sine wave defined on this purple trace, and I have a different sine wave defined on this blue trace. And then this red graph is the exact same, is this expression right here, this equation 5, where I have the f function of the difference minus the f function of the sum. So what you see is, let me make this a little bit more obvious. So what you see is you have one sine wave with a frequency of 1, and you have another sine wave with a frequency of 3. And the result is you have actually let's make this 1.2. That's a lot more obvious. Okay. This term here has a frequency of the difference of the two. And so if we look here, that's only a frequency of 0.2. So this is 1.2 minus 1. And so we get, this is the main period that you see right here. And then a much faster period, which is the sum of the two. So that's m equals 1 plus m equals 1.2. So that's f. So you have one sine wave, which is 0.2, and then you have another sine wave, which is 2.2 on this graph here. And I can adjust any of these parameters. It'll tell me the evaluation of this integral. This is at some point x, you're integrating over the last cycle from x of this product of the sine waves, and then the result is red curve here. So a couple of interesting things to note is that if we make the two sine waves the same, so the same frequency and the same, okay, here, I'm actually going to graph, but what I have graphed here is instead of the sum and the difference, I just have this function f. If I make m1 go to 0, then we're just left with a straight line, okay? So the first thing to notice is that when the frequency of the sine wave goes to 0, this is just a straight line. So in normal RMS calculations, when your sampling period of the RMS is the same or an integer multiple of the 60 Hertz line, then it doesn't matter where in the cycle you start sampling, consistent throughout the entire sample. Another thing to see is that if this is not 0, so let's make this like 1, then it's just a sine wave expression. So this f function is just another sine wave. It's the same frequency as the original, but it's different amplitude and it's different phase shift. So if I change my original phase shift, it's the same phase offset as the original. Okay, now one interesting thing that can happen when our sampling is the same frequency as the 60 hertz line. So for example, let's do a pi and a pi here. Notice that we get another DC offset because this term here with the difference contributes to DC offset, and this term here with the sum goes away.
You got a frequency of 0.
Right. So this one has a frequency of 0. This one has a frequency of 2 times the sign, and so basically this term in the F expression makes this vanish. So when your RMS period is a integer multiple of the 60 hertz line, this term vanishes and you're just getting a DC offset. But when so let's say instead of 5, we make it like 3.5, then we get something very, very different from that. All of my results about what is happening with this expression here, this is detailed in all of these paragraphs. So this paragraph talks about how you're always getting a difference frequency and you're getting a sum frequency. So if you start with a 25 hertz and a 40 hertz, you're going to end up with a 15 hertz signal, which is the difference of the two. You're going to end up with a 65 hertz signal, which is the sum of the two. And then when the two input waves have the same frequency, you have a DC offset here, and then you have a frequency which is double. So let me show you that here. So if I make each of these, let's say 3, notice that when both frequencies are 3, then we get a DC offset, and then we get just a pure sine wave of double the frequency. So this is oscillating twice as fast as the main frequencies. So we're just getting pure DC offset, and then we're also getting a pure sine wave. Let's see, when the two input waves have the same frequency m and the same phase shift, then this DC offset that was cosine of the difference, that just becomes 1, and then you just get 1/2 for the DC offset. That's when the two phase shifts are aligned. And then this paragraph talks about how because of this 2-factor, pure sampling is a multiple of 30 hertz, then it also goes away. So a frequency of 2 pi for each one makes this flat line. But if I make it sine of pi, which is half, then it just goes to a flat line as well. That's what this paragraph is talking about. This paragraph says that interharmonic signals, which are basically when you have a signal present on the line which is not an integer multiple of the 60 hertz, when that is present, then you don't get this nice cancellation out that all of your variation goes away. And so we're basically left with this equation 6, which is where I'm substituting in this result into this expression into equation 2. So I'm solving this interval in equation 2, and then the answer is equation 5, and then I'm substituting that into equation 6 right here to get the result. And then I've done a worked example. So my red signal is a 120 RMS signal. So this is your standard 120 volt signal. I have a 5% signal at the third harmonic, and I have a 3% signal at the fifth harmonic. That's in the red graph right here. And then for blue graph, I have the same as the red, but I have an additional 2% signal at 175 hertz. So this is just a little bit off from this 180 hertz signal. So with this example, I've gone through this calculation. This is the h of t that we're talking about. And then we're going to substitute this to equation 6 into this equation right here. And we're going to compute all of the sums and all the differences and all the product of the waveforms. So plugging this in directly, we get this whole expression right here. So you get basically from this parentheses all the way down to here. And then after doing as many simplifications as we can do, all of the places where we get a 60 hertz part. So for example, like this term right here is going to go away because it is a direct integer multiple of 60 hertz. But what you're going to be left with is all of this simplifies down into all of this, where you get all of these terms, this term, all of those come from just the DC part of each individual sine wave. And then you're also going to get a bunch of the sums and differences. So you get a 115 hertz component right here. You get a 235 hertz component right here. You get a 5 hertz component right here. You get a 355 hertz component here, 125 components right here, 475 right here, and you get a 350 hertz component right here. So I've went ahead and plotted all of those together. That's in this black graph here. It's basically just oscillating very quickly between two different sine waves. This is a low frequency 5 hertz sine wave right here, and this is a low frequency sine wave right here that are offset by just a little bit. This expression describes how the RMS of this signal is changing at any point in time over the last cycle of measurement. So we're computing the RMS over a single cycle of the 60 hertz line. So you can see it. There's a lot of high frequency variation, but the problem that we care about is the low frequency 5 hertz signal. Because if you notice, it's going from down here, which is minus 0.4% roughly, up to up here, which is roughly 0.41%. So this is oscillating 5 hertz basis between 1.0041 times 120 and then going down to minus or 0.9996 of 120. So it's very quickly oscillating between this point here and this point here on a 5 hertz basis. And one of the problems that you see with that is that the flicker standard, so this graph is from the IEEE standard 141 that describes, so this curve here is the borderline of visibility for flicker. So you have dips per second, dips per minute, and dips per hour. So this is the tolerable limit for what is noticeable. And then this line here is the limit for what is irritable and very, very annoying to look at. And so with this example, our red dot, which is, we have we're oscillating about 0.45%, or basically we're oscillating 0.5% in RMS over a 5 hertz basis. So our 5 hertz line is right here, and we're right about half, and that's well inside of the borderline of visibility curve for the IEEE standard. So with this particular example, it would be very, very obvious. It would be very annoying to look at with lights. Just an example of how interharmonic variation we just have just a little 2% signal. So 175 hertz, we're injecting just a little bit of extra signal into the power line, and we get a massive variation in the RMS, which would lead to a massive problem with flicker.
Basically, yeah, the key here is that if you have these non-synchronous frequencies in harmonics, you're going to get variations in RMS voltage that are very quick. Here, like Landon said, we're at about 5 hertz. Anywhere between the 2 and 10 hertz range is where people are absolutely the most sensitive to flicker. So as you can see in this graph, if you're in this region, the allowable limit before you see the threshold of irritation is really small. We're way under 1% is the limit. It's more like 0.5%. That's not a lot of RMS voltage variation allowed. And it's easy to get that kind of variation when you have even just small levels of these interharmonics because of the way they create a very rapid variations from cycle to cycle. Unlike harmonic components, which even though harmonics are waveform distortion, they're the same RMS value from cycle to cycle because they're synchronous. And so harmonics may produce other problems on the power line, but they're not going to introduce flicker like these interharmonics do. Well, if you have any questions about the paper, feel free to give us a call anytime at 1-800-296-4120 or send an email to support@powermonitors.com. Thanks for attending, everyone. Everyone have a great day.